Hello and welcome to AlgoSavvy. In this video, we will learn the application of Kadane's algorithm. This is a very popular algorithm and a very common interview question. This algorithm was devised to solve maximum sum subarray problem. Before talking about the algorithm, let's try to understand the maximum sum subarray problem. In this problem, we are given an array and we are asked to find a subarray which has the maximum sum. A subarray, in the context of this question, is a non-empty subarray of contiguous integers of the parent array. For example, if we have 1, 2, and 3 as the main array, then the subarrays will be 1, 2, 3, 1 and 2, 2 and 3, and the array itself 1, 2, and 3. One thing to note here is all these subarrays are contiguous arrays. So we will not see 1 and 3 in the list of subarrays. Let's take another example. In this example, I have -4, 3, -1, and 7. The subarrays that can be derived from this array are -4, 3, -1, 7, -4 and 3, 3 and -1, -1 and 7, -4, 3 and -1, 3, -1, 7, and the array itself -4, 3, -1, and 7. The question is asking to find the array with the max sum and return the sum. In the given examples, the sums of each subarray are 1, 2, 3, 3, 5, 6. In this example, the subarray which generates the maximum sum is 1, 2, and 3, and the sum we need to return is 6. In the second example, the sums that can be generated from the subarrays are -4, 3, -1, -1, 2, 6, -2, and 5. So in this case, the subarray that generates the maximum sum is 3, -1, and 7. And the sum that we need to return, the maximum sum, is 9. So the question is asking us to return the sum and not the subarray itself. That can be another flavor of this question. But in this question, we will concentrate on only the sum. The main thing to observe here is that if we have all the positive numbers in the input array, then we can directly return the sum by adding all the numbers. The complexity increases due to the presence of negative numbers, as we can see in the second example, where we have two negative numbers in my input. Due to negative numbers, we need to figure out all the possible combinations of the subarrays. It might still be easy to figure out all the possible combinations if there are only 3 or 4 numbers in my array. But if the size of array increases, the possible combination of the subarrays will increase exponentially. That's why Kadane's algorithm is very important for this particular problem, which solves this problem in linear time complexity. Hopefully, now we understand the question and what is the subarray and what is the maximum sum subarray. Now let's talk about Kadane's algorithm. Kadane's algorithm uses dynamic programming to solve this problem. In this approach, we need to iterate through each number of the array once, and we need to calculate what is the maximum sum that can be generated at that iteration using the current number. For example, if we are at -2, what is the maximum sum that can be generated from the start of the array till -2 using -2? So since this is the first number, the maximum sum that can be generated using -2 is -2. Now, when we move to 1, we need to see using 1 what is the maximum sum that can be generated? For that, we look into the previous maximum sum that was generated. So the previous maximum sum that was generated is minus 2. So if we add 1 to minus 2, it will give me minus 1. But 1 itself is bigger than minus 1. So I can ignore this minus 2 and I can say that I am self-sufficient to generate the maximum sum at this particular position. I will say at this position, the maximum sum that can be generated is 1. Now, when we move to minus 3, we again check with the previous sum which was generated. So the previous sum which was generated is 1. And if I add 1 to minus 3, it will increase the value at that position. So either we can take minus 3 itself, or we can add minus 3 to the previous sum that was generated. So if we add minus 3 to 1, it will give me minus 2, and minus 2 is greater than minus 3. So I can write minus 2. Then when we move to 4, we'll again check by adding 4 to the previous maximum sum that was generated. So 4 and minus 2, if we add, we get 2, which is lesser than the value of 4 itself. So we don't need to add the number. We will just say that at 4, the maximum sum that can be generated is 4, and so on. So going by this pattern, we can derive a formula. And the formula will look like max sum at I is equals to max of array at I, or the sum of array plus at I max sum at I minus 1. So this is the formula which we can use to generate the maximum sum at a particular index. Either it can be the value itself or value plus the sum, the maximum sum that was generated for the previous index. So using this formula, let's complete our dry run. So for minus 1, we will see whether minus 1 is greater or minus 1 plus 4 is greater. Minus 1 and plus 4. Minus 1 and plus 4 gives me 3, and minus 1 itself is minus 1. So 3 is greater than minus 1. So I'll get 3 at this position. Now at 2, we will compare again whether 2 is greater or 2 plus 3 is greater. So 2 plus 3 is 5, which is obviously greater. So we will write down 5 here. At this position, again, we will check whether 1 is greater or 1 plus 5 is greater. So 1 plus 5 is 6. We will write 6 here. Then at this position, we will check whether minus 5 is greater or minus 5 plus 6 is greater. Minus 5 plus 6 is 1. Obviously, 1 is greater. And then for the last number, we will check if 4 is greater or 4 plus 1 is greater. So 4 plus 1 is 5, which is greater than 4. So 5. Now we have got the max sums which can be generated at each index. So now we need to find out which is the maximum of this max sums. Okay. So by looking at these numbers, I can clearly say that the max sum which can be generated is 6. So the subarray which is used to generate this max sum starts from 4 and it goes to 1. So certainly we know that it ends here, but this particular formula doesn't say that where it started, but there is a tweak that we can do to find out that as well. That is currently out of scope for this question. Let's proceed. By looking at this approach, we can think that, okay, we can use another array to store the max sums for each index and then go through this array to find the maximum value after this loop is done. But that approach, we will be consuming an extra space of n. So what we can do is, instead of using the array, will store all these values in a temp variable, the max sum at I, and we will use another variable, max sum so far, to keep track of what is the maximum value that was achieved till now. We will be populating both the values in the same loop. just one after the other. So when we get a maxsum, I will check what is the value at maxsum so far. Is this maxsum greater than maxsum so far? So currently it is not initialized. So we will say -2. Okay. So when we go to 1, is 1 greater than maxsum so far? Yes. So we will populate 1. Then for -2, is -2 greater than 1? No. So I'll say 1. At 4, is 4 greater than 1? True. So I will change it to 4. Similarly, is 3 greater than 4? No. So I'll continue with 4. Is 5 greater than 4? Yes. We'll update 5. Is 6 greater than 5? Yes. We'll update 6. Is 1 greater than 5? No. We'll continue with 6. Is 5 greater than 6? No. We'll continue with 6. And then in the end, we will return max sum so far. Whatever the value is there in max sum so far, we will return it. So in this way, we will not be using any extra linear space to store the maxsum at I. So let's talk about the time complexity for this approach. Since we are iterating through this array only once, the time complexity will be big O of n, and space complexity will be big O of 1. Constant space because we are just using two variables, maxsum at I and maxsum so far. So this is the conceptual overview. Let's proceed to the code walkthrough. Welcome to the code walkthrough of Kadane's algorithm. We have the method signature defined. We expect an array of integers, and also we need to return an integer which is representing maximum sum subarray. So as discussed in the conceptual overview, let us first declare the variables int maxsum at I. We will initialize with the first value of the array because the maximum sum that can be generated at the first value at the first index is the value at the first index, right? So we'll simply assign it 0, and then the maxsum so far variable that also will assign array of 0. Then we'll define the loop I equals to 1, I less than array dot length I plus plus. We'll declare a temporary variable to store the value at index I. And now we need to update our maxSumAt I. So maxSumAt I is equals to maximum of array at I, which is num, or num plus maxSumAt I. So here we are checking whether the number is greater or the sum of number and the previous maxSumAt I is greater. And here itself, we will be checking for our maximum sum so far. So maxsum so far is equals to math dot max. We will check it against maxsum so far itself and maxsum at I. In the end, we'll just return maxsum so far. Okay. So it's a pretty straightforward solution. We are iterating through each of the numbers once. We are initializing the maxsum at I and maxsum so far with the first value of the array. And at every iteration, we are updating these two variables, maxsum at I, maxsum so far, with the formula that we discussed in the conceptual overview. For maxsum at I, we are using math.max num or num plus sum. And maximum sum so far, we are just comparing with the previous maximum sum and the maxsum at I. And we are returning maxsum so far in the end. So as discussed, the time and space complexity, time complexity is big O of n, as we are iterating n times, and the space complexity is big O of 1, as we are using only 2 or 3 temporary variables. Thank you for watching. Hope the code walkthrough is clear. For any doubt, please put it in the comments. Let's meet in the next video. So friends, if you like the content, then please like the video and subscribe and share the channel with your friends who are preparing for interviews. See you in the next video.